Let us start this lecture with a thought process. What we do generally, although we spend our entire life for seeking external comfort by acquiring gadgets, particularly in modern days, but internal comfort dictates the extent of external comfort. Question arises, how can we achieve the internal comfort? And if you look at previous lecture, we are basically discussing about how to get comfort and also avoid the vagaries of the weather conditions, right? And if you look at, we started with basic laws of how to handle the non-reacting mixtures, right? Like Dalton's law of partial pressure, Amagat's law, and then we moved into looking at only how to handle or analyze the moist air, because that is the thing what dictates the comfort level for a person, and then that is the basis of the air conditioning, right? So if you recall that we define a term which is known as specific humidity, right, which is nothing but the ratio of the amount of water vapor and the air, amount of mass of air in a water or vapor air mixture or wet mixture. We call it as also moist air, wet air. So and that we had expressed in terms of also the partial pressure. If you remember that specific humidity is equal to 0.622 PWS divided by PA, right? That is the thing what we looked at it. Now question arises, how much amount of moisture the air can contain, right? And that will be dependent on the temperature, right? Yes or no? So we'll see as we go along, it will be dependent on temperature. You might have experience, right? If temperature is very high and it is humid, you are feeling very uncomfortable, particularly in this season nowadays where the rain is knocking at our door, and then like we get, and temperature also is quite high. And if it is, you can bear that temperature, let's say 40 degrees Celsius. If the moisture is not there, it is dry, it is not that uncomfortable. You might have seen. So now we need to evaluate basically how much moisture, air can, can carry or at a particular temperature. And in other words, you can say what is the capacity of the air to hold the water vapor, that way. So for that we will be defining a term which we call basically relative humidity, because there is a capacity of air to hold some amount of water. Beyond that it can't, right? And that will be related to the saturation, point. So therefore, we are defining a term which is relative humidity. It is the ratio of amount of water vapor in the mixture to the amount of water vapor in the saturated mixture at a particular temperature and pressure, right? So if you look at saturated what you call water vapor, what it could, you can get from the steam table, saturated steam temperature table you can use, and you can get what will be the partial, pressure of that, and also, from that you can find it out, what will be the amount of moisture, because if the temperature, you know the pressure, you can use as the ideal gas, you can find it out. So, very easily. So that is RH is basically, RH is nothing but your relative humidity, which is nothing but amount of the water vapor in a moist air divided by the maximum amount of water vapor the air can hold at that particular temperature and pressure. So, and by ideal gas law, I can write down m dot Wg is nothing but Pwg in the volume, of course, the molecular weight of water divided by Ru. Ru is the universal gas constant, T, right? T is the temperature. So that is from the ideal gas law. And similarly, the amount of maximum water vapor a moist air can hold at a particular temperature and pressure can be written at Pws, V, molecular weight of water divided by RUT. So if you look at, all will be cancelled out, this will be cancelled out, this will be cancelled out, and this also will be cancelled out. What remains is the, is the partial pressure of water vapor in a moist air divided by the saturated water vapor partial pressure, right? Saturated means beyond that it cannot. And that sometimes we call it as also phi. I mean, both the symbol are same, relative humidity and phi, right? So it, as I told earlier, basically it is dependent only on the two pressure, partial pressure. One is the partial pressure of the water vapor, right? And other is the partial pressure of water, right, at saturated condition, right? So in the of the dry air mixture. So you can relate now the specific humidity to the relative humidity. What we can do, we will take this, relationship that we know, that is SH is equal to 0.622 Pwg divided by Pa, and we know that Pa, partial pressure of air, is nothing but P, the total pressure, minus Pwg, right? And in place of, I can write down Pwg divided by Pws into Pws, I can replace that, and this is nothing but your what? That is your RH, right? And Pwg, this I can write down as RH, is equal to RH Pws. So therefore, SH is nothing but 0.622 RH into Pws divided by P minus RH Pws. That means, you can relate this, specific humidity with the relative humidity, right? So you can have that once you know one of them and you know the temperature. So if you know the temperature Pws, you can find it out from the saturated steam table and corresponding to saturated condition, right, and the temperature. And then of course you know the atmospheric pressure. Generally air condition, when we are talking about atmospheric pressure, this is P is basically atmospheric pressure. Then you can very easily find out specific humidity, right? And vice versa. If you know the specific humidity, you can also find out the relative humidity, provided you know the temperature at which you are working. So in the similar fashion, I can write down an expression. RH is equal to SH into P divided by 0.622 plus SH hold the bracket Pws, right? So that is from this relation, just I have rewritten, that's all, nothing else more than that, okay? So now we need to understand the dew point temperature, right? So what do you mean by dew? You might have observed, right, particularly in the summer season, if there is a moisture in the air, right, what happens? Particularly in the early morning or in the late night, the temperature will be dropping down. If it drops down, what happens to the moisture? You might have observed, Baba, like in your day-to-day life, right? You have not seen the grass is having a lot of water, it contains water, in the early morning. Of course, you people are not getting up early morning, not going for a walk or a look at the beauty of the Mother Nature. So, you are devoid of that, or deprived of that, rather, not devoid, rather deprived because of your own lifestyle on an average scale. I am not saying all of you are like that. So, please change your lifestyle, it is very important because life is more important than anything else. So, coming back to that, that means you will get some water which is condensed, and of course, you need a surface to be condensed, and that what you call grass or leaves and other places, you will find. So, that is nothing but your dew point or the temperature. Why? Because in the summer, the temperature will be high. If there is a pond or a water bodies, of course, water bodies are receding at an alarming rate, not only in cities, but also in the rural areas. So, if it is there, then a lot of evaporation will be taking place, right? Okay. And if evaporation will take place, it will be there in the air, atmospheric air, and we call it basically moist air, right? And that will be condensed back. Having said this thing, let me ask another question. What are the differences between the evaporation and boiling, which we had seen in the boiler, in the earlier also steam and other things, pressure cooker, also we boil the water, steam comes out, several places. What are the differences? Any idea? Any idea? No. I am expecting that you should, have some ideas. What is the difference? Because all are evaporation of the water is converted into its vapor. In the case of your, what you call, evaporation, and also in boiling, right? So then what are the differences? Is there any differences, or there are no difference at all? What do you think? Both are, change of phase from liquid to its vapor, particularly the water, what we are considering at this moment, right? What are the differences? Let me tell you that it is, I'll tell you briefly because, of paucity of time. See, the water evaporation always take on the surface of the water level. Let's say in a pond, right? It will be evaporated, right? And if it is evaporated, then there will be, of course, it depends on the vapor pressure, what it is having, and then we'll try to nullify that, changes. Because away from that, it will be having concentration gradient, that will be the driving force. And in case of boiling, the temperature on the bottom surface of the wherever you are giving heat, heating surface, right, there will be very high, higher than what will be happening in the evaporation, right? And then the bubble will be formed, right? And the bubble will go up, and then there's the steam will be formed, and then that is the boiling, right? You won't call unless bubble form. Am I right? Yes or no? But in evaporation there won't be boiling. There won't be any bubble formation, right? So therefore there is a lot of difference. Temperature here it will be higher because interface temperature between the water and the metal or any other hard surface, will be very high. But there it is dependent on the very, whatever temperature it is having. So there are, more subtle points you can look at it. So I was telling about the dew point. Dew point, you can think of conducting experiment in your room itself or in your home. So what you can take, I can take a, what you call a glass of the water and little bit ice on it, so that I will drop the temperature, and stir it. So I can measure this temperature till the outside of the glass. Either it is, if it is a metal, it will be good. Even in your glass, or a tumbler, what you call this is a tumbler basically. And even if made of glass, it will be having bubble. You might have seen. Suppose you take something from the freeze and keep, on the table just to let it cool down, you will find lot of moisture in the outside. From where it has come? It has come basically from the atmosphere. Like whatever the air will be in contact with the surface of the tumbler or any other container, right? It will be just condensed because it has reached a temperature that is known as dew point temperature, right? Before that, before it reach, the water won't condense. So therefore, we can define the dew point temperature as the temperature, right, at which condensation begins if the mixture is cooled, of course at a constant pressure. If pressure changes, that is, but we are assuming that to be remaining constant. This example, of course, pressure will be remaining constant and you are not mixing it very vigorously, right? And what is the meaning of that? That is basically the temperature of the water, saturated temperature of the water, right, or this thing at a constant vapor pressure, right, we call it basically dew point temperature. If you look at in this TS diagram, this two-phase, like process, you are here somewhere T1, and as you, cool it, so that you will be moving towards that, temperature will be down. At this point, what will happen? This is what you call vapor. This is your, what you call the saturated vapor line. This is saturated vapor line, right? Saturated vapor line. And at this point, it will start condensing, right? After that little bit, this thing, it will be start condensing. That is the point at which the vapor will start formed, right? No, sorry, it will be only vapor, but it's a point at which the vapor will be started condensing, right? So that point, we call it as a dew point temperature. So we look at now the adiabatic saturation process, where, if it is saturated and no heat being transferred, we call it as a adiabatic saturation point. So let us consider that there is a moist air which is entering into this adiabatic saturator, right? That means no heat is going out here, zero anywhere, right? And it is having certain temperature, right? And of course, this is the moist air. It will be containing certain amount of air, and also it will be some kind of vapor. It is having some specific humidity, let's say station 1, so therefore I am giving SH1, and relative humidity. And then when it will come in contact with this liquid water, what will happen? There will be some vapor, water vapor will be going, like this thing, something water vapor will be, right, carried over by this air, and in such a way that it will be long enough, right, so that it will be giving you the point here that it will be saturated almost, or saturated. Saturated means it cannot take more than amount of moisture at the temperature. Of course, there will be some drop in temperature, right? Yes or no? Because it's carrying evaporation, therefore there will be some, heat of vaporization has to be given, and that will take care. So therefore temperature will be dropped down. Of course, the liquid level will be coming down. We will give some amount of liquid here such that this level remains same, right? And what happens to the relative humidity? What happens to the specific humidity at the exit of this adiabatic saturator? What will happen? If it is saturated, from the definition of relative humidity, we know, which is nothing but the ratio of mass of water vapor divided by the mass of water, saturated mass of water. So therefore it is same. So RH will be equal to, RH2 will be equal to 1, right? Okay. So do you find this application anywhere? See, if you go to Fatehpur Sikri, right? You have gone to Fatehpur Sikri, the fort, you please visit there. Earlier days, this was very hot also at the same time. They were having this kind of channel, water channels, right? That which will make it cool. The king or the queen or the other people will be in comfortable zone, right? Okay. So you can see in our ancient time, people may not be knowing that much what we are talking in the class, but they know how to design and develop. Okay. It is not only that, you can go to earlier fort, several fort, whatever we are having, you will find a lot of science and technology there. So let us now look at that how to analyze it. As I told that if the mixture becomes saturated, and in this case we are giving enough length of this water or allow the water to come in contact with the air which is entering into the adiabatic saturator, such that it will be saturated at the end of this. So then the mixture at its exit is termed as the adiabatic saturation temperature. Right? Are you getting? The temperature, whatever it will be attained, let's say this is T2, right? This temperature, right? T2 is there already, okay? This temperature T2, then that temperature is basically the adiabatic, what you call, saturation temperature. Okay? So is it different than that of your dew point temperature? Yes or no? Will it be different or will it be same? So we will see that. You please think about it. So we want to analyze this, right? What we will do? We will be doing standard assumptions, that is steady flow process. Change in kinetic energy is 0. So also change in potential energy is 0, right? And there is no shaft work. Are you giving any shaft work or some power? No, no, right? So there won't be any shaft work. Shaft work will be 0. So what we will do? We will basically do two things. One is your mass balance, other is your energy balance, right? And this is a flow process. Therefore, we can take a control volume, right? We can take, this is my control volume, right? Okay, this is control volume. So I can consider, like 1, 2, station 1, 2, and also we are giving some amount of water, and generally this water is given, in such that this is liquid is at temperature T2, right? That is being supplied, and such that it will be, the label will be maintained. Otherwise, analysis will be difficult, and also then it won't be very effective, like, because water level will go, then water air has to come in and take it, it will be difficult. So, and why this water has to be given? Because it will be evaporated. If it is evaporated, the level will go down over a certain period of time if you operate longer period of time, okay. So by mass balance between the inlet and exit, this is station 1 is your inlet, station 2 is your exit. What we will do? We will basically look at this mass of air at station 1 is equal to amount of air, that is the mass flow rate of air at station 2 is equal to mass flow rate of air, because nothing more is added. There is no addition of air in this, through this port at the station 3, right? So therefore, that is not. And whereas for when we do the water balance, right, what is that? Mass flow rate of water at station 1 plus mass flow rate of water at station 3, because you are giving some water, is equal to mass flow rate of water which is going out of this adiabatic saturator. Make sense? Right? This is just a mass balance, right? So we will similarly do the energy balance, and that is summation of the enthalpy is equal to summation of the enthalpy at the exit. This is the inlet, left hand side is inlet and right hand side is your exit. And if you look at how many inlets are there here, in this case, there are 2. One is station 1 and station 3. And exit is only 1, that is station 2. So by that we can write down this energy balance, that is m dot A1 into HA1, that is the enthalpy of the air which is entering, right, plus m dot Wg, that is the water vapor mass flow rate, into Hwg at station 1 plus the amount of enthalpy due to water which is entering into the into this channel liquid what you call container, right, and is equal to the amount of enthalpy which is exiting out from this adiabatic saturator, that is m dot A2 into HA2 plus m dot Wg2 Hwg2, that is the enthalpy due to water vapor, right. So, we will basically club this kind of values from the mass balance and then simplify it, right. If I divide this thing by m dot A, right, whole m dot A1, this will be cancel it out, and this is A1 and this is m dot A1, this is m dot A1, right, m dot A1. Right. We know that m dot A1 is equal to m dot A2, right. So, therefore, this will cancel it out, right. This will be 1. Why? Because m dot A2 is equal to m dot A2 from this air we have done. So, similarly, here also we can write down m dot A2. So, what is this term then by definition? This term, what is this? This is basically SH2, specific humidity, yes or no, right. Similarly, this if you look at, this will be SH3, one can say, and similarly of course here we can say very happily that is SH1, right. And this you can say SH3, right. So, if you look at from this expression, right, you can get that what you call from your this expression, right, we can get MW3, right, is equal to MWA1 SS2 minus HS1, right. Will you get this one? How I will get this one? What I will do? I will just do that m dot A1, we will divide at m dot A1 in that m dot A1, and this is nothing but your SS2, and this is nothing but your SH1, right. Okay. So, from this I can get MW3 is equal to, from this expression I can get MW3 is equal to m dot A1 SS2 minus SS1, and m dot A1 is nothing but m dot A from this equation 1, right. Are you getting? So, now, so if I divide this equation as I told, this is coming, and that is MW3, we have already seen that is nothing but your MWSH1, because we have seen that MW3. So, if you look at like what I am doing here, and this is from equation 3, we get that HA1 is nothing but SH1 HW1, and this MW3 here, if you look at, I can get basically I can use this expression here, I can get SS2 minus SH1 into SW3 is equal to HA2, right, from this expression plus SS2 HW2, right. And if you simplify this thing, I can get SH1 is equal to HA2 minus HA1 plus, because I will take this side, right, and SS2 I can take to this side, right. So, SS2 SW2 you can take to this side basically, to this side, SS2 into SW2 minus SW3. Okay, what I would basically, what you will do, you can take this what you call SS2 side into one side, and then SH this one, and then you can SH1 you can take to one side, and then you can get this relationship, that is specific humidity is equal to HA2 minus HA1 into the SS2 in the bracket SW2 minus SW3 divided by SW1 minus SW3. So this is the expression what you can get for the specific humidity at the station 1. So if you look at, if I know these values, right, HA2 and HA1, and if you can find out SS2, because we know the relative humidity, right, and we can find out this HAW2 and SW3 and SW1, SW3, then we can very easily evaluate the SH1. So, because if you look at SS2, we know already that 0.622 PW2 divided by P2 minus PWG2. And if you look at that this SW3, what we can say that it is corresponding to the what values? That is nothing but your HWF2, right? Because that is the thing what we are saying, at the same temperature it will be saturated liquid. So therefore, at temperature T2. So if you can look at this portion will be nothing but here, if you look at HFG2 at T2, right? And this way, similar way, I can replace this thing here with the HWF2, right? And I can also write down this thing, because if you look at, this is about the air, and I can say that Cp is remaining constant, it's not changing with the change in temperature. So therefore, I can write down that what you call SH1 is equal to Cp T2 minus T1 plus SS2, that I was telling HFG2 divided by the HW1 minus SW2, right. So if you look at, if I know these Cp values, right, and that is for a air you can take 1.005 kilojoule per kg Kelvin, and T2 and T1 is if you know that temperature, right, so then you can find it out easily, and SS2 you can find out very easily provided you know the temperature, right. And HFG already you can get from the steam table, and all these values you can get, and then we can calculate very easily. So if you look at that, as I was telling, that this is the dew point temperature, where the temperature is changing, and there also that thing. But whereas the adiabatic saturation temperature, take this path, it will be different temperature, because the heat is being not going out, therefore there will be little higher temperature as compared to the dew point temperature, right. It is not going out by that thing. So what we will do, we will see how we can basically apply these equations and finding out the various properties. We will take this kind of an example. We can take an example and look at it. But before that, let us ask a question: what do we mean by psychometer? Because we want to find out this the dew point temperature, and then what you call dry bulb temperature and kind of thing, so that we can find out what is the relative humidity, what is the specific humidity, and other things. So and if you recall that we had discussed about wet bulb temperature, that is the temperature which will give you basically corresponding to the moist air, right? And if we can have a device for this, like we can think of using, like air here, right? Air is going, and when you will just put a thermometer, whatever the glass bulb thermometer we are having, that will give me the dry bulb temperature, right? But if I will, put into a liquid, and then of course this is a cotton or a wick, whatever you use, and is moist air, so therefore that will give me the wet bulb temperature. Of course you need to suck the air at a particular velocities, right, so that it won't get affected, and then it will be this thing. That is the laboratory what people use to have a very precise measurement of the dry bulb temperature and the wet bulb temperature, right? And this is known as psychrometer, because once you know this, you can find out very easily what is the relative humidity, what is the specific humidity, right, and kind of things, and you can know. So of course, if you look at this wet bulb temperature, depends on the rate of mass and energy transfer, right, and of course the radiation heat transfer from the surrounding, and kind of things. One has to take care of that. But here it won't be, because you are keeping, and then this temperature won't be that much, so that there won't be radiation. There is no other heat sources, and we will see that this can be done very simply using a thermometers, which we will be discussing in a very simple way. And on the other hand, if you compare this dew point temperature with the, or what we call this thing, saturation adiabatic temperature, is dependent on the equilibrium between the two phases, thus is a property of the system, right? Okay, therefore the saturation adiabatic temperature is basically the property of the temperature, and which will be closer to the what we call dew point temperature, right? And for a air water mixture of a PA, the wet bulb temperature is quite closer to adiabatic saturation temperature, right? Wet bulb temperature is closer. And if you look at, that is a complex system what I looked at, but if you might have seen these thermometers in your laboratory and other thing, there is a one thermometer here which will give me the dry bulb temperature. So this will give me dry bulb temperature, right? Okay, that is the dry bulb temperature, right? And this wick is there, which you will have to put moist it, like, or the cotton, that if it will measure, that will give me the wet bulb temperature. This you might have seen in any laboratory it will be having. But however, it may be not giving the right temperature for the wet bulb. Say what people do, like they will have to swing it, you will rotate it, so that there will be some velocity of the air which will be coming, and then there will be some vaporization will be taking place, and water, and so that heat will be taken out, and then it will be temperature wet bulb, it will be saturated, right? So that this kind of things, and it will give you the wet bulb temperature. And let us see how we can use that. We will take this example. Let's say a sling thermometer is used to measure and dry and wet bulb temperature of air at 100 kPa, and the dry bulb temperature is 40 degrees Celsius and wet bulb temperature 30 degrees Celsius, and we need to find out specific humidity, relative humidity, and enthalpy of the humid mixtures. And keep in mind that this the thermometer which is rotated, we call it basically the sling thermometer. This is known as sling thermometer. Right, and this is being used to measure that. Now, how to go about this thing? So, if you look at, it is given, right? What other things are given? The dry bulb temperature dV is given 40 degrees Celsius, right? And wet bulb temperature is given as 30 degrees Celsius, right? And of course, the pressure is given 100 kilopascal. And to find, we will have to find out SH, RH and also HM, the mixture of the humid air, we need to find out enthalpy. So, how to go about? You can say that, as I told, that this is the sling thermometer, but we can assume that is a basically saturated adiabatic mixtures, right, kind of things. So, if we do that, and what is given here, if you look at this T1 is equal to 40 degree Celsius, right, and the T2 is equal to 30 degree Celsius, it is given, right, and we can find out enthalpy at the basically SH1, we need to find out what is the moist air is entering into saturated adiabatic saturator, right. So, what we will have to find out basically that by considering adiabatic saturator, right, at temperature is equal to 30 degree, right, and we can find out the SH1, we have already seen SH1 is equal to Cp T2 minus T1 plus SH2 HFG2 divided by the HW1 minus HF2, right. So, if you look at what is T2, T2 is given, this is given, right, 30 degree Celsius, T1 is given, Cp of course you can take as air Cp, that is 1.005 kilojoule per kg Kelvin, and we need to find out SS2, this is not known, right, we need to find out, and HFG2 we will have to find out, SW1 and HF2, all those things we need to find out. But how to go about them? How we will get SS2, let us say, because we know that RH2 is equal to 1, right, okay. That means it is saturated condition at station 2, right, RH2 is equal to 1. That means the PWG2 is equal to PWS2, that is saturated condition. Now, if I know these things, right, okay, so I mean like we can, and that is what is happening, that is basically at what? At 30 degrees Celsius, right. So, if I know RS2, can I find out the SS2, right? I can find out very easily, right. So, let us take the properties of this, because I need to know this. Why? SS2 we know is equal to 0.622 PWG2 divided by P minus PZ2. Now, what is this PWS2? That if I know this, then I can get very easily, that is equal to that, okay. PWS2 is equal to PWG2, partial pressure of the water vapor at station 2. So, for that we need to use the saturated steam table. So, from saturated temperature, right, steam table at 30 degrees Celsius, what we can find out? We can find out all these properties, that is PWS is equal to 4.246 kilopascal, and which is equal to PWG2, and HF2 I can find out 125.77 kilojoule per kg, and Hg2 is 2556.25 kilojoule per kg, right. And let us also look at the from the saturated steam table at 40 degree Celsius, right. PWS is equal to, that is of course S1 is equal to 7.384 kilopascal, and Hg1 is 2574.26 kilojoule per kg, right. So here I can put these values, that is basically 0.622, and we have taken that pressure is 100 kPa, right. Generally people take 101.325, right, 101.325 kilopascal, but here it is given, so you need not to take atmospheric pressure, right. And PWZ is basically what we call 4.246 divided by 100 minus 4.246, you will get the value is basically 0.028 kg of water per what? Kg dry air. That means SS2 is equal to 0.08 kg of water it is carrying per 1 kg of water, right. And if you look at, now we can substitute these values, all the things we know now, okay. Is it, do we know? I think I made a mistake, this is G1, right, just check that. So we know this is nothing but your H1, right, this is now known, HF2 is known, right, and this HFG is nothing but what? HFG2 is nothing but your what you call 2556, Hg2 minus HF2. Okay, let me write it down. So I can evaluate SH1 is equal to Cp is 1.005, T2 is equal to 30 degree minus 40 plus HS2 is 0.028 into HFG, basically Hg2 2556.25 minus 125.77 divided by Hwg1, that is 2574.26 minus 12577. So if you do this, you will get basically 0.023 kg of water per dry air. And once we know this SS1, I can find out what is RH1, right? Can I find it out? Very easily. What we will do, we know SH1 is nothing but 0.622. Of course, you can use the other formula, but we can use this is simpler one, G1 minus P minus Wg1. And from this, because we know this value, this is SH1 0.023, then I can get PWZ1 is equal to basically 3.67 kilopascal. So RH1 is nothing but your PWG1 by PWS, which is, what is PWS? 1? What is that? That is nothing but your 7 point, this is this one, 7.384. You will get basically 0.497. Okay. And we need to evaluate now HM1, that is nothing but HA1 plus SH1 HWG1 is equal to Cp, that is 1.005 into 40 degrees Celsius, plus SH1 we know that is basically 0.023 into the HWG1, that is nothing but 2574.26, and which will be equal to 101.2 kilojoule per kg. So, what you can get is basically, like all these values. Question arises, you will have to do all this calculation to find out these properties, but is there any other simpler way of doing that we are going to do? How we can use a chart which is very quickly to find out, and then we will see in the next class. Thank you very much.